Hi, I'm Ben-Yaakov. This presentation is entitled Autonomous Active Dissipative Energy Cell Balancer. There is a reference here, it's a paper. I'm going to print the details at the YouTube page of the video that you are now watching. So we're talking about serially connected energy storage cells, for example, electrolytic capacitors. Sometimes you need a higher voltage and you like to use a capacitor with a lower voltage. So this will be safe for typically, if you want, say, 600 volt, it might be better to use two 400 volt capacitors, and you like to put them in series in order to get the voltage of each capacitor in the safe region. Supercapacitors have a low voltage, so in order to get a high voltage overall, you need quite a number of these in series connected as an array. And also batteries, for example, lithium-ion batteries, which are about 3 to 4 volts. If you need a higher voltage, you do have to connect them serially to get the voltage that is needed. So why do we need to do the balancing? Well, there are two aspects to it. First of all, to prevent damage. Many energy storage elements will be damaged if the voltage of them is too high or too low. For example, a lithium-ion battery, you should not discharge it to a lower voltage than a given limit. On the other hand, there is another problem here, and that is optimal energy utilization. If you have one of the cells of low energy content, that is lower voltage, then it will determine the energy capability of the whole array. So if you need the pump out energy of this array, it'll be the limiting factor. So you'd like to make all the cells having just about the same energy level. So this is the reason why we do have to do balance. In this video, I am discussing a method which is explained or presented in the paper that I've cited. It is active dissipated balancing. It is active in the sense that it is using active devices. That is, that it uses transistor or maybe amplifiers, but it is dissipative. That is, that it is actually wasting energy. What it does is that whenever there is a cell with a high level of energy stored, as compared to the other, it'll dissipate it. It'll actually convert it to heat by discharging the cell, which has a higher energy level. This method can be used for a variety of energy storage cells, like capacitors, supercapacitor, and I think over for lithium-ion, but I'm going to describe it in connection with capacitors, let's say supercapacitors, but as I've said, it can be modified and used for batteries like lithium-ion battery. I'm not saying that this is the best solution. However, this is one possible approach, and I think the most important part is that one can learn a lot from this idea behind this method. So one of the features of this method that we are going to discuss is it is autonomous. That is, it doesn't need any control circuitry or processor in order to operate it. It'll do it by itself. And let me show other possible ways of doing it. For example, if I have capacitors and each capacitor has some leakage here, this represents the leakage, then obviously at steady state the voltages will be different, so the energy stored will be different. So one way to stabilize them will be to put resistors, a resistor divider. Obviously the current here has to be higher than here so as to override the effect of the leakage. So this method brings about quite a bit of power loss. There's another way, and that is to limit the maximum voltage by sort of a, say, Zener diode. And there are some units or some balancer which are using, in fact, a MOSFET connected like this. This is like a Zener diode, because once the voltage here exceeds the threshold, then this will start conducting. So therefore, what will happen here, that this method will limit the voltage so it will not exceed the maximum. However, if one of the cells has a lower voltage, it will not correct it. So that if you need to discharge this energy into a load, then this cell with the lower energy will be kind of a limiting factor. So this method does not balance, in fact, only that it is keeping the voltage below the dangerous level for the element that is used here. Now, the method that I'm going to discuss is again described in this paper. This is the heading, the title of the paper. It is authored by Ertl, Wiesinger, and Kolar. It was published around 2007. So here are possible implementation of the idea that is described in this paper. There are actually three circuits here. One which is based on a operational amplifier, a BJT transistor, and MOSFET. I will primarily concentrate on the transistor, the BJT transistor solution, and also the operational amplifier. I think in the MOSFET there are some issues here, and I think it's less desirable. Now, it's important to realize that this circuit will balance the unit such that the cell of the highest voltage will be discharged until it reaches the value, the voltage of the other cell, which of the lower voltage. So eventually the two voltages will be the same by discharging the one which has a higher voltage. Now, what happens if we have a large number of cells in the array? Well, we can put a balancer for these two capacitors, and then another balancer for these two, and then another balancer for these two. So what will happen is that all the cells will eventually reach the voltage of the cell with the lowest voltage. So all will be equal to the voltage of the cell that was to begin with the lowest voltage. This is very similar to the method of passive discharging by resistor or transistor and resistor, which is normally referred to as passive balancing. But then, in this case, you do have to control the transistor, while here the balancer is self-operating without a need for an external control. So let me start with this unit here, which is based on two transistors, NPN and PNP. This divider is a 1-to-1, so the voltage here is half the voltage, the total voltage, and the difference between this point here, that is the midpoint of the capacitor in this case, and the divider is the difference here. This is V1 plus V2 over 2, it's the voltage here, and then I subtract V2, and I'm getting that this voltage is then V1 minus V2 over 2. So if V1 is larger than V2, then this will be positive, and then if V2 is larger than V1, then this will be a negative voltage. So now, in the case of the transistors, if V1 is larger than V2, then we have here voltage which is higher than the voltage here, so therefore this transistor will be conducting, and consequently it will start to discharge this capacitor. Now we can represent it by Thevenin equivalent circuit. This will be the voltage at this point. This is the internal resistance. So this is the circuit that is operating now, and as long as the voltage here is lower than V1 plus V2 over 2, because V1 is still large, it will discharge it, continue to discharge it, until these will come to be equal. And the current that we're going to have will be this voltage difference minus VBE divided by this resistor is the base current, and times beta is the total current of the collector or emitter within alpha. So here is the expression for this current, beta times this difference here divided by the equivalent resistance of this Thevenin circuit. Now what happens if V2 is larger than V1, that is V2 is larger, then we get a negative voltage, and therefore the PNP transistor will start conducting, and it'll be very similar. Again, this is the equivalent source, and this is the internal resistance, and then the discharge will be like this, so we'll be discharging V2 until it'll reach the value of V1, and this voltage here will be equal here. Well, all this is within, of course, VBE, so this is not very accurate. We have like a plus minus VBE hysteresis here, or a window here, so it's not a very precise circuit. The behavior can be represented by this graph for the current. This is the voltage. This is the voltage difference. Until we reach VBE, nothing is happening. Once we reach VBE, then the current will start going up with a slope, which is this slope. So this is the slope of this curve, and of course it is linear with this difference between V1 and V2, the absolute value. Now what happens if we are putting here, rather than two transistor push-pull, an amplifier, an operation amplifier? Now obviously this amplifier will start to react when there is a voltage difference here at the input. That is, when half of this voltage is different from the point here. So if V1 is equal to V2, R1 equal to R2, everything is fine. But if V1 is larger or V2 is larger, then we start having here a voltage. Being an operational amplifier, it'll kind of move to the extreme. In fact, it'll go into saturation. And then you will have either a current like this or a current like this, and I'm showing it here, while here is the region when V1 is just about equal to V2. Now the current here is limited by the amplifier in this case, and it is a function, of course, of the voltage here. That is, for a higher voltage it's a little bit higher, but it's just about like a constant current. This will be the sourcing current of the amplifier, and this will be here the sinking current of the amplifier. If the current is insufficient, then we can of course put a buffer here, a push-pull, and then push it again. The feedback will be taken from here, so we are not bothered by the VBE. And in this case, the current, of course, will be approximately, depending on the amplifier, whether it's a rail-to-rail, etc. I'm not going into this details. I'm assuming that the drive is strong enough so that we have approximately the voltage over RB will be the discharge here, and the voltage over RB will be the discharge here. So this is for small changing. Otherwise, you have to take into account that the total voltage, of course, is changing. There are some issues that want to take into consideration, and that is that we're not talking in general about a DC situation. In general, we would expect current to be passing through this capacitor, if I'm just showing a change in the current. And if the ESR of these two capacitors is not equal, and if the capacitor in fact are not equal, then the voltage here will not be half the value of the total voltage, because again, if the capacitor or the ESR are not equal. In this case, we'd like to avoid the back and forth switching here at the output, so one way to do it is to put some filter. This is by no means optimized. There are of course many other ways to do it, but we are interested in the average value, the DC value, so we'll have to somehow filter out these changes so as to not to cause this amplifier to switch back and forth whenever you have current flowing to the system. So let's have a look now how this thing will work. So suppose we have a capacitor which is at a higher voltage than all the rest. Suppose all the rest are the same, so they are the same, this one has a higher voltage. So what will happen is that by this balancer, this will discharge it, this balancer will also discharge it, so the voltage of this capacitor will go down until it will reach, of course, the same value as the neighboring capacitor, and then the discharge will stop. If, however, this unit is connected to a outside source, a power supply, then of course, although the voltage will drop, then there will be a recharging of the whole array, such that again the voltages will be the same, but correcting it to a higher voltage. If we have one cell which is of a lower voltage, say all the other ones are the same voltage, this is of a lower, then what will happen is the operation will start by discharging this one, this neighbor here, and then this one here, and then since this will be discharged, then this will also be discharged, and eventually all these will be at the same voltage, balanced out, as again will be the case with a passive balancing system with transistor and resistor that are controlled by some central control unit. Again, if the unit is connected to an outside supply, then obviously the voltage will be recorrected so that the total will be equal to the input. So just to demonstrate the operation, I've prepared a basic LT-Spice model here. What we have here are three capacitors. These are three capacitors. Now we have two balancers here for this pair and this pair here. I'm going to show the current here, the voltages of the capacitor, as well as the error voltage at the input of these two amplifiers. Okay, the simulation starts with these voltages. This is 3.5 volt, this is 4 volt, and this is 3.3. So the whole thing is not balanced. And the purpose here, of course, is to make the voltages equal. Now I'm using here a model of a capacitor, which is composed of a capacitor and a voltage source. Okay, a charged capacitor can be modeled by a voltage source of the initial value of the voltage plus a capacitor with 0 voltage on it. This is equivalent to this. I'm using it because it's easier to set the initial condition here by changing the voltage of these voltage sources. So this thing is actually representing a capacitor, 100 millifarad, charged to 3.3 volt initially. And here is the simulation result. Let's start with the capacitor voltages. We have one which is about 3.3, and there is another one, and then we have one which is about 4 volt. As one can see, the capacitor with the higher voltage starts to discharge until it reaches the voltage of the next higher capacitor, and then the two of them are being discharged until they are reaching the value of the capacitor, the voltage of the capacitor with the lower voltage. Here we see the current. This will be of the model that I'm using, the maximum current coming out of the amplifier. We see here one amplifier and then the other amplifier. And here we see the error signal at the input to the amplifier. It starts off with fairly large error because of the differences, and then as the balancing goes on, it sort of tapers on, and eventually it sort of comes to be a very small value when the system is balanced. Here is a zoom of this, and this is when everything is balanced. What we see here, let's start here with the error signal. It is small. This is depending, of course, on the model, LT-Spice model of the amplifier. and it's about, I don't know, 3 millivolts, the two amplifiers. And here is the current. This is just a zero line. So this is the current of one amplifier. It's say 0.5 milliamp, and this amplifier. And then here we see the capacitor voltages, which are very, very close. This is a 10 millivolt difference. It's say 10 millivolt difference. Of course, this is a function of the amplifier, the offset of the amplifier, and this can be improved if indeed required. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.